this is Further Mechanics 2, the sample paper from so the first ever paper they wrote, I guess. When we're doing this kind of question, we just need to integrate the formula here for the unit length thing between, for the length that the thing goes on for. Just integrate between 0 and 15, and you eventually just get that that's 105. So I won't go into too much detail here, but eventually you do get 105. You can verify that all of that's good. Find the distance. So we just use this formula essentially, where y is representing this stuff. Now, of course, if y is just this, we've already done this bit, and this is just 105. And then we also just put this in for here, but we also times it by another x, so that integral is going to be slightly different. I've just put this 105 over here just to clean up some space here. Of course, integrate that, you end up with a quadratic. You integrate the quadratic, which you ends up with a cubic. And yeah, I'm not gonna do too much of that. The calculator will just get that done for you. The 105 divides again, and you end up with this. So very nice, easy first question. Number 2, this length here is a, clearly. This length here, which we're going to need later, we can use similar triangles for that. Like this is 4a across and 4a down, which means if this is 3a down, this is 3a across. By similar triangles, halve that down to get 3 over 2a. Now, of course, if we call this angle alpha, I think tan alpha is 4a over 2a, half of this, which is just 2. Which means I think that, look, considering a little triangle here, tan alpha is 2 over 1, which is 2. Do some Pythagoras to work out that's root 5, so therefore sine of alpha is 2 over root 5 and cos alpha is 1 over root 5. Of course, you could just inverse tan to find alpha and use that, but this is more grown up. Good, so this is also alpha, which I'll use later by corresponding angles. Moving on a little bit, we have a reaction force that's, of course, perpendicular to the surface, as we've got a little mass in here moving around. So the mass means mg, of course, going downwards. And now we need to set up some force stuff going on. Let's do up and down first. Now the up forces. Now this force upwards, the component of r going upwards. This angle here is 90 minus alpha. So opposite that is sine 90 minus alpha. But sine 90 minus alpha is the same as cos of alpha. So upwards is our cos alpha, which equals mg. Plus, before we get that far, we've got some friction going on as well, of course. Sorry, we've got some friction going on. Now, if we're maximizing omega, maximizing the angular speed, that means that the thing is going to try and move up the slope, so therefore friction is acting down the slope. Friction, of course, just being mu r, and mu is a quarter. So that's down the slope. So now we've got some forces to resolve, sorry. So I already said that going upwards, we've got r cos alpha equals mg plus, and now if this is just alpha here, the component going down from there is just alpha is opposite, so it's sine alpha going down, so a quarter sine r sine alpha. So we've got r cos alpha, as said, equals mg plus a quarter sine r sine alpha. We can, of course, put in cos alpha and sine alpha into here and solve for r. We eventually get this. And now we can resolve forces going to the center just using F equals ma, where the acceleration towards the center is omega squared times the radius, which is 3 over 2 of the circle that it's traveling on. And of course, we've now got some horizontal forces to deal with. We've got 2 of them. We've got r sine alpha going inwards this way. Of course, if that was r cos alpha, this is r sine alpha, so that's there. We've also got a plus a quarter r cos alpha this way. So that's those 2 forces going towards the center equals ma, where again a is omega squared times the radius, which is this, and we can sort this all out because we have r, and we also have sine alpha and cos alpha, and so I'm going to be fairly quick about this, but we end up with that eventually there, and that will be the all of question 2 done. Excellent. Question number 3 is a center of mass question where we've got a mass here and a missing mass here. This is what the formula book tells you about our solid hemispheres. Center of mass, that's going to be helpful. Obviously the center of mass of the cylinder is just a half h down from the top, because that's h, and we're thinking down from the top here. The center of mass of the cylinder is, of the sphere, hemisphere, is 3/8 of a down from the top. And now we just use this idea where we need the volume of the cylinder, which is just pi times 2a squared times h, which is this, and we also need the volume of the hemisphere, which is half of 4/3 pi a cubed, which is 2/3 pi a cubed. And we'll do this thing where we have total volume is this minus this, because of course this bit is missing. Total volume times x bar, which is really probably a y bar, considering we're working vertically, but I don't care, is equal to the distance of the center of mass to the first object center of mass times that volume, minus, because again it's a missing volume here, the distance there to times by that one's volume. We'll sort this all out. There's some very sort of subtle things you have to do to try and make it into this. Always keep your eye on the prize. For example, well, firstly, a squareds can all cancel. But now I'm noticing I need an 8h squared minus a squared. So let's times all this by 4 to make that into an 8 and that into a 4. That seems sensible. It also gives us some stuff over here. Now, I need an 8 into this stuff. So if I times all this by 3, and in order to put a third on the outside, so I've sort of factorized out a third, I guess. I can actually times by 3 to make this 3 here, which is good. And I can also factorize out an 8 from that, which will give me the whole thing as wanted. So always keep your eye on the prize, and it wants it like that. Good. Now we're on rest on a slope. We know the height. Now we've just worked out the center of mass, the combined center of mass from the top. So therefore, from the bottom, the combined center of mass is h minus what we just found out. So that goes there. H minus that is the distance from the bomb to the center of mass. And now for this to tip over, the vertical vector downwards from the center of mass would need to get to this corner here. Now on my picture it of course doesn't, but let's just pretend that it does. If it did, it would need to be, this distance here from here to here would need to be 2a. Now of course that's not in my picture, but of course we can imagine rotating this up, making phi bigger and bigger, rotating it up, and then eventually this would vertically come down to here, and we'd end up with 2a. The picture is irrelevant though, of course, because all we have to say is that tan phi is this over that. So let's do that. We're told h is 5a, so we can substitute 5a into there, and then you can factorize out an a from here and factorize out 2a's from, or a squared from there. That cancels, and then they'll cancel with this final a up here. You can do a bunch of other maths in your calculator to find this, and then of course the a's all cancel, like I said, do tan inverse, and you get this as your answer. Good. Question number 4 is when we have the two formulas for f equals ma. The first is f equals m dv by dt, because of course that was all a is, and that's the first one we'll use here because of course they're asking for t. Let's put in f, that's 1800, take away this, equals this, with m being that. Let's do a separable differential equation here, I guess. I've divided everything by 2 just to make it a bit easier. This doesn't really integrate easily yet, but I think it will do if I do some partial fractions, because it's a difference of 2 squares. I'll do some quick partial fractions over here. I will not spend much time on this. You solve partial fractions however you want. You'll find a and b as this. We can put that in, and now I think I'm ready to integrate. This integrates to a 1 over 250t. This integrates to a 60th of log of this. No, it doesn't. Yes, it does. A 60th log of this, but with a minus as well, because that derives to minus 60v. So that's where the minus a 60th at the front comes from, log of this, and this is just a 60th log of this thing here. You can just factorize out a 60th first if you want to, and then yeah, you just get all this. Plus c, of course, because you've done some integration. Of course, log laws say that because this is the minus, so it can be log of this divided by that. I've times everything by 60 and cancelled out the zeros there, which is fine. This c here is now solvable because we know it accelerates from rest, so when v is 0, t is 0. But when v is 0, you get log of 30 over 30, which is log of 1, which is 0, so c is 0. So we just end up with this just without the c, which is great, because that's shaping up nicely to be this. When v is 10, t is big T, so put those in. You get 40 over 20, which is just 2, and then of course times by 25 divided by 6, and we end up with this. Show the distance from O to A is that thing there, so now we're talking about distance. So we need f equals ma to be f equals mv dv by dt, v by dx, sorry, of course, because we need an x in here. Of course, we do exactly the same thing. It's a separable differential equation still. I've divided by everything by 2, and then I've divided everything by 125. Now, the reason I've done that is because that leaves behind a 2v, which means now this thing derives quite nicely into this, just without the minus. So I think this integrates to just minus log of this, which is nice. Plus c again, this integrates of course to just that. C, well, we know that when t is 0, we're at the origin, so x is 0 when t is 0. We also know v is 0 actually, which is more relevant. V is 0 because it's from rest. So we put those in, and we get c as, I think, just log 900, because that goes away, just move this over. We get this, so we have this now as our formula. Now, distance from O to A, now we're at A when we're moving with this speed, so we put in 10 into here, and 900 minus 100 is 800. Of course, we can divide these logs as we did before to just get log of 9 over 8 times by 125, and we end up with the thing that they wanted us to get. Question number 5 is basically identical to question number 3. I don't know why they've done this. But anyway, you've got a missing area here, and you've got a whole area here, and we need to find a combined centre of mass. So I think that far sounds familiar. So of course the centre of mass of this rectangle is just A across and 2A up, and the centre of mass of this sector is going to be this. Now this angle here is of course pi, which means we need alpha to be pi over 2. Put that into there, we end up with this. The radius is just A, of course, we get this. So that's the distance from here across to there. So as a coordinate, you could write it like this from, pretending that's the origin. You actually don't need to. I typed that and then realized I didn't need it, so we can basically just ignore this. But that's the center of mass of this one up here. Now, okay, what do we do here? Well, of course, we just need the areas. So the area of the rectangle is this times this, which is that. The area of this is, of course, pi r squared, just halved, with r being a, so that's going to be that. Now we use the same formula, so total area is this minus that, equals the distance from this one's center of mass, which is just a, times its area, and then minus the distance. We're going from AD, but that's still a across this way, isn't it? So that a still holds, and then distance across from here is just 4a over 3 pi, but we're working from this side over here, which is why this is kind of irrelevant. Times its area, and then we sort this all out. It's so similar to question number 3, we've got to get it into this form. Again, you do a similar sort of trick I did before, cancel the a squareds, times everything up to try and make these nice whole numbers. I'm not going to go through it again in very much detail. You end up with it eventually, and we'll have that done. Now next it's saying, so we've got our combined centre of mass here, and we know this distance across is what we just found out. Now next it's saying it's being held from 2 ropes going upwards, with 2 different tensions of course. It's asking us for the tension in B. To do that, we can just find moments from A, or take moments from A, because if we take moments from A, we can ignore this tension, because of course it's a distance 0 from A. So taking moments from A, we have that 2A times this tension, which is the clockwise moment, is equal to this distance here, times by the weight coming down, which we just called as W. So we have taking moments A, this, W, times this distance is equal to 2a times that, divide by 2a, and we end up with this. Just cancel the 2 and the a there, and that's all that is. Now the rope neck for the next question. The rope at this breaks. So the rope at B breaks, so it's just hanging from A, which of course means that it's going to hang through the center of mass like this. So it's going to tilt across. So this is a vertical line, and we're told that tan alpha being this. We're told tan alpha is that, and we're trying to find this distance here. Now to do that, we need to find the distance from here to the center of mass there. So we just need to do exactly the same as we did before, but with all the y sort of coordinates. So we say the total mass is still this, or the total area really is still that. That should really be a y bar, but whatever, I don't care, is equal to 2a. Now 2a is the distance from BA. I'm taking this from BA because I want to know this distance. 2a is the distance from BA to the rectangle's center of mass, because that's of course in the middle, and then D is the distance, this distance here, to the center of mass of this semicircle, because of course it's just straight across from there somewhere. So okay, that's all the same thing I've done there. We'll sort this out, we'll do some doubling and stuff and divide. So that's not really x bar, that's this distance here, really I should say y bar, down from BA, which means of course I can put that in. And now I can say tan alpha is this over this. The 16 minus pi's cancel, which is nice. I think that's why they encourage you to get in that form in the first place. Tan alpha is 11/18, so I'll put that in. And now we do some cross multiplying and some other stuff, and we'll actually end up with D in terms of A being that. And we're done. Good. Question 6 then. So we've got a mass threaded into a hoop. It's going to initially move with this speed, and then it's going to get around some way and move with another speed, and we're being asked what speed to show that speed there. Now of course the only thing going on here is conservation of energy, I believe, to start with at least. This angle is theta with the downward vertical. So initially it's got the only energy it has is a half mv squared kinetic energy, because there's no tension going, there's no string or anything here holding any energy in. If we consider this to be kind of ground level, it's got no potential energy, so we've just got its initial kinetic energy is equal to its final kinetic energy plus mgh, and we just need to find out this h that it's risen. Of course, to do that, we can just call this length here a, of course, is the radius. So this here is a cos theta, because it's next to the angle, which makes this distance here, because that whole thing is a, is just a minus a cos theta. So there's the energy balance equation. We could just put in this h here. We could cancel a load of m's and other things as well. And we rearrange and we end up with the thing that they wanted, which is good. Find the size of theta of the instant. The contact force is 0. So we've got a contact force of r usually here. We've of course got an mg coming down. Now, it's not going to be here where r is 0. It's going to, as it comes around, it's going to be up here where it loses contact force, but I couldn't be bothered to redraw the picture. It doesn't really make a difference, of course. Resolving forces here towards the centre, F equals ma, we've got r, and now we've got to get this force obviously in the same direction. So here we've got mg, now that's theta, draw yourself a little triangle going, closing up here with a right angle there. The hypotenuse is mg, next to it is mg cos theta, of course. That's mg cos theta if this is theta. Just closing up the triangle there. So r minus mg cos theta is equal to v squared over r, v squared over the radius, which is just a, because we've not been given angular speed this time, but just actual speed. So that's going to be, that's the formula there, F equals ma. So okay, r is 0, and we also know v squared is this thing here. R is 0 because contact force is 0. So we get this, or we can just cancel the m's and the g's and solve for cos theta here, I hope. We end up with, eventually, theta is that. So like I said, theta is 120, means it loses contact force up here somewhere. Explain why this is realistic, just do the usual things and say the usual things that you always say in this case, and yeah, that's fine. Find the magnitude and direction of the acceleration at the instant it's at rest. So we have a formula for v, so let's just set v to be 0 if it's instantaneous rest. So let's set that to be 0. Of course, this can't be 0, so let's just solve this thing. And we get this, which we solve to be, at some point I'll find out theta, but not right away, because, so it's moved around here, it's somewhere up here, I guess. Cos theta is 3 over 4 means this triangle. I was just being fancy, and I don't know why, so I was doing this thing to get sine theta. And then what I said was, if you're at rest up here somewhere, your acceleration towards the center is going to be 0, because if your velocity going round is at 0, remember that acceleration towards the center was v squared over a, but of course if your velocity is 0, as it is, then that means there's no acceleration towards the center. So we only have acceleration tangent to where we're going, which means that we can set up F equals ma tangent to the circle. So of course, tangent to the circle, we've got the mg sine theta. So going back to this triangle here, mg sine theta is the force tangent to this, and that's the only a that we've got left over. So we've just got tangent to the circle is F equals ma, is this, sine theta is that. So I was being fancy and just found a exactly. You could of course have just found cos inverse, which I'm about to do in a second. Cos inverse of this is this, and so we're 138 degrees away, which we could have just used to find this other bit. But anyway, we also need the direction of the acceleration, which we know is tangent to the circle, but let's find exactly where that is. So 90 minus this gives me this angle to the horizontal, being that. Now acceleration, like I said, is this way. We can do a downward vertical here, and of course if this is, let's just call this alpha, 90 minus alpha, this is a right angle here as well, of course, so that's going to be alpha there, which is just this. And so we can say the acceleration is maybe 48.5 degrees from the downward vertical, or something like that will be fine. You could have also gone around and done from horizontal or whatever, and found the other one, but that's whatever. Cool, so we've got simple harmonic motion here at 6 meters apart, two things. We've got two strings of length 2, so these are being stretched quite a lot to make up a gap of 6. We've got the particle in the middle, of course. We need to find its equilibrium point first. Always, when you're doing simple harmonic motion, find the equilibrium point. So we're going to say T1 equals T2 for equilibrium. Of course, Hooke's law says this thing here, up here, the moduluses are this. So we can just find the extensions in terms of each other. So the natural length are both 2, so that's there. So we get that x is 2.5y. So the stretch in the first string is 2.5 times the stretch in the second string. Now, how is that helpful? Well, again, if the gap is 6 and the two natural lengths are 2, that means that the stretch together is making up a distance of 2. So the two stretches together make up a distance of 2. And then, of course, we can just substitute this result in and find that the stretch in this string is 4/7, which of course means the stretch in the other string is 10/7. And now we can do some simple harmonic motion stuff. So the two forces like this equal mx double dot is fine. Now, what's T1 if you're just at some random place in the simple harmonic motion? Well, the usual stretch in T1 is this, and then we're just going to add in a little stretch of x going this way, maybe, and so we get this. And then in T2, the usual stretch is 4/7, and we're going to take away a little stretch in x if we're going this way, if we imagine. So that's going to be take away x. So plus to one of them, minus the other one, because one has to be stretched more for the other one to be stretched less. So that's cool. M is this, apparently, and all of it cancels. You get this and you get this, which is good. So it's simple harmonic motion with omega squared being 10. So that's excellent. So that's the 7 marks there, I guess. Good. Find the maximum speed of p. So this is a super useful formula to know that I think you should just have memorized. Maximum speed happens when x is 0, when you're in the middle of the simple harmonic motion. So of course, if you put x as 0, you get v squared equals omega squared a squared, which just simplifies to v equals omega a, which you could just memorize as well to find max speed. Of course, a is it's initially held 2 meters from b, but 2 meters from b is just the natural length of this string here. So it must have been moved, if its equilibrium position was that stretch of 4/7 across, it must have been moved those 4/7 back again to get to its extended point here. So okay, that means a is 4/7, which I can sub in with the omega that we found before, and we get in a calculator this. And then find the length of time for which we're closer to a than b. So let's be clear about this then. So 2 is the natural length of this string, plus 10/7 gives us an equilibrium point of 24/7 from A, and exactly the opposite, 18/7 from B. The amplitude is 4/7, which means, of course, that we need to go 3/7 in this direction to balance those out and be in the middle. So using this formula here, because we start at one of the ends, so we use the cos formula, we just need x to be minus 3/7, because remember I was taking x to be positive this way before. So we need x to be minus 3/7. We have all of this information, so we're just going to find that for t. And of course, actually, we can find 2 values for t when we do cos inverse, because it's going to go from here across to here. That'll be our first t, and then it's going to go back here and then back again, and that'll be our second t. So we can just do cos inverse to find this, and then we can think about the cos graph if we want to, and do, I haven't even bothered to do it, but I just thought about the cos graph for a bit, or do cast diagrams, however you've been taught. Find the other solution that you get, the next one, you get this, divide both by root 10, you get that, and of course the first time is the one that gets to there, and the second time is when it comes back again, so the time in between is just the bigger value, take away the smaller value, and that will be the entire paper done. Thank you for watching.